A discrete random variable x takes on the values little x1, little x2, little x3 up as far as little xn, with probabilities p1, p2, p3 up as far as pn. As an example, x could be the value showing on the throw of a fair die. So the values x1 up to xn will be the numbers 1 to 6. So n would be 6. We would have 6 discrete values, and they would happen to be the numbers 1, 2, 3, 4, 5, 6. And the associated probabilities would all be 1/6. The probability of getting a 1 is 1/6. The probability of getting a 2 is 1/6, and so on. So we use a capital letter for the random variable and the corresponding small letter for a specific value that capital X takes on. Now, the probability that X takes on the value x1 is little p1, and so on. The probability that x equals x2 is little p2. The probability that x equals xn is pn. Now, x must take on one of these values. So the probability that x is equal to x1, or x equals x2, or x equals x3 as far as x equals xn must equal 1. So it's a certainty that x takes on one of these n discrete values. Now also, these events are mutually exclusive. So if x equals x1, it will not equal any of the other values. If x equals x2, it will not equal any of the other values. So x can only one of these events can only occur at a time. So that means that we can add the probabilities here using the OR rule. So this is equal to the probability that x equals x1 plus the probability that x equals x2 plus as far as the probability that x equals xn. But the probability that x equals x1 is written p1, and this probability is written p2. The last one is pn. So the sum of all these probabilities is 1. Now we can also write this using the sigma notation. This is the Greek letter sigma. It's an uppercase sigma in the Greek alphabet. So we're summing all the probabilities denoted pi, where the subscript I runs from 1 to n. So this sum equals 1. Now, in another video, we will discuss continuous random variables as opposed to discrete. If x is a continuous random variable, that means it takes on values in a continuous range. So you could imagine x taking on, say, values from 10 to 13. So this would be a continuous range. So x could be any value in this range. We're not dealing with that here. We just have a discrete set. When we throw a coin 2 times, we can have 0 heads showing, exactly 1 head showing, or 2 heads showing. These are the only possibilities. X must take on these values. So the sum of the probabilities must equal 1. So it's a certainty that x takes on one of these values. Let's write out the sample space. If we throw a fair coin twice, we could get 2 heads. We could get head first, tail second, tail first, head second, or 2 tails. So we have 4 equally likely outcomes because the coin is fair. What's the probability that no heads appears? Well, let's look at that event. That event has just one element in it. So we just have one element over the number of elements in the sample space, which is 4. So we have 1 over 4. Or we could work this out by multiplying a half by a half. The probability of getting tails is a half. And we're dealing with independent events. So we multiply the probabilities for each throw of the coin, each of the 2 throws, to get a quarter. Now let's look at the probability of getting exactly 1 head. Well, that event consists of these 2 elements. So we put the number of elements in here, which is 2, over the total, which is 4. So we have 2 over 4, which is a half. Finally, we have to consider the probability of getting 2 heads. Well, that's this event here. It just consists of 1 element, so it's 1 over 4. We can see that these probabilities add to 1. Now, as for notation, capital X takes on these values. We denote each of these values by little x. So little x1 is one of these values. It doesn't matter which one we call little x1. We could call this one little x1. Then little x2 is the second value, and little x3 is the third value. So we've 3 discrete values here that x can take on, and here are the corresponding probabilities, P1, P2 and P3. Here is another example of a discrete probability distribution table. In this case, the random variable x is the number showing on the roll of a fair die. So x takes on the values 1 to 6. Since the die is fair, the probabilities are all the same. Now x must take on one of the values 1 to 6, so the sum of the probabilities must equal 1, of course. And all the probabilities are the same, so each one is 1/6. So as far as notation goes, x1 is one of the values it takes on. Let's say little x1 is 1, x2 is the second value, little x2 could be 2 in this case, x3 is say 3, or whatever we want to call x3, it doesn't matter. And the corresponding probabilities would be little p1, little p2, little p3, so on.